Recall lecture 13, we talked about probability models, uh, where probability model was a procedure that you could repeat as often as you liked, where the outcome was uncertain, where the outcome was uncertain. A random variable is just an example of a probability model in which those uncertain outcomes are numbers. So here are some examples. We'll generally refer to random variables using capital letters. We'll name them by capital letters. So I'm going to give you some examples. I'm going to give them names and refer back to them. So the first one, which we'll call x, is rolling a die. We saw that when you rolled a die, the possible outcomes were the numbers 1 through 6. Because those are numbers, that's a random variable. If you flip a coin, flip 4 coins, and count how many heads, that's a repeatable procedure, uncertain outcome, outcomes are numbers, so it's a random variable. Let's call it y. The possible values go from 0 to 4. If you pick an adult at random and ask them how many children they've had, the answer is a number, so that's a random variable, which we'll call z. And finally, each time you go running, the time it takes you to run is an uncertain outcome, which is a number. So that's a random variable. The first three, x, y, and z, are discrete. The possible values are integers, nothing in between, but the last one is continuous. Any real number is, positive real number at least, is potentially a time for your run. We will see that that discrete versus continuous distinction, which didn't really matter in anything we did with numerical variables, will become very important, especially from a theoretical point of view, from our way of describing random variables. Example Z is a particularly important example for us. Going forward, for us, the most important random variables will be ones that, like Z, involve a population and a numerical variable in the sense of lectures 5 through 9. The random variable is randomly selecting an individual from the population and measuring or asking the value of that variable. So from this point of view, numerical variables and random variables are two different ways to look at the same thing. Everything that we did with numerical variables has an analog. Sometimes it looks a little different in random variables. Here the emphasis is on probability. Very much like we saw in lecture 13, we were talking about events and independence, and in examples, it looked a lot like when we were talking about the relationship of categorical variables, independence and things like that. And we found different calculations ended up getting to the same place. So when you talk about a discrete random variable, you've given all the information you need if you just say what the possible values are and what the probabilities are. So we'll describe a random variable mathematically by just a chart that lists the values and their probabilities. When we just talk about that information and ignore what it's modeling, we call it a distribution. And a little piece of notation, if I want to talk about the probability when you roll a die you get 4, I'm going to say that P parentheses x equals 4. That's the probability that x equals 4. Okay? And now I have to make an embarrassing confession about the notation, which will look kind of ugly here. More than just notation, the word variable used in probability context means something a little different from variable in mathematics. Remember, in mathematics, a variable is just a name you give to an unknown quantity. It could potentially have any number as a value, and it's just a question of substituting that value in. Random variables, because they have this probabilistic aspect, are really a little different. So random variables are represented by capital letters, usually late in the alphabet, like X, Y, Z. Ordinary mathematical variables are usually written with lowercase letters, often late in the alphabet, X, Y, Z. But unfortunately, these will clash because sometimes we'll want to talk about an arbitrary value of the probabilistic random variable. And if we want to name that potential value, we'll use a mathematical variable. So we will often talk about the random variable x and some arbitrary value of it, little x. And we end up getting expressions like p parentheses capital X equals little x, meaning the probability of getting a certain number x in your distribution. This is just unpleasant. Don't let it upset you. Okay, so let's do some examples. This will be less abstract. When you roll a die, the variable we called x, there are 6 possible outcomes. The numbers 1 through 6, each of them we saw had probability 1/6. So this is what our table looks like. Notice, because a random variable is a probability model, all the probabilities, all the second row, will be between 0 and 1, and they'll all add up to 1. Just like you can check something as a probability model without worrying about what it models, you can check something as a random variable by checking all those probabilities are between 0 and 1, and they add up to 1, without worrying about what it models. Flipping a coin, flipping 4 coins, is a little more complicated. How do we find the probabilities there? Well, you have to enumerate all the possibilities. I've done that below. There are 16 things that can happen when you flip 4 coins, because 2 possible outcomes for the first flip, 2 for the second, 2 for the third, 2 for the fourth, and you multiply those 2's together to get 16. And now when I ask what's the probability that we get 0 heads, I just have to go through and count up how many of these possibilities have 0 heads in them. There's only one. The only way to get 0 heads is to flip 4 tails. So the probability of 0 is 1 divided by 16. The one way divided by the 16 possibilities. Pause the tape here and work out the others and make sure you're getting the same thing as me as a check that you're following. There are, 4 different ways that you can get 1 head and 3 tails. You can get the first coin as a head, or the second, or the third, or the fourth. So the probability of getting 1 head is 4 out of 16. We go through and count up the 6 ways of getting 2 heads. So that's 6 out of 16, and then notice they repeat. Getting 3 heads is the same as getting 1 tail, which has the same probability as 1 head. And likewise, 4 heads is probability 1/16, just like 0 heads. Okay, that was an interesting example. The next one is empirical. There's no way to calculate how many kids people have. You have to go and ask them. I'm going to use, for my empirical data, the General Sociological Survey. This is a really valuable resource that you need to know about. If you Google General Sociological Survey, you'll come to a website and you can download data on just about any question you can imagine. This is a survey done every year by the Sociology Department at UC Berkeley. They ask a very large sample of Americans a huge array of questions about everything you could imagine that has to do with sociology somehow. They ask people their marital status, how many children they have, what their beliefs are, what their activities are, what their work is like. It's a wonderful treasure trove of data, and in particular, when you're considering group projects, you should think about using this as your source of data, finding variables on the General Sociological Survey that you can relate. You can download the data, do the calculations yourself, and then and that could be a perfectly nice group project. Anyway, once you have a distribution, we have 3 sitting in front of us, you can answer any question about probabilities very straightforwardly. For example, if you want to know the probability that when you roll a die, you get more than 2, so we write that probability x is greater than 2, you go to your chart for x, you look at all the values which are greater than 2, that would be 3, 4, 5, and 6, and then you add up all the probabilities beneath them. 1/6 plus 1/6 plus 1/6 plus 1/6 is 2/3. Now you try each of these to make sure you've got it. pause the tape as necessary. What's the probability y is less than or equal to 2? That is the probability when you flip 4 coins, you get 2 or fewer heads. Well, there are 3 ways: 0, 1, or 2 heads. The only possibilities, you add up those probabilities, you get 11/16. What's the probability that someone has more than 1 child but fewer than 4? That is that z is greater than 1 and less than 4, which we write like that. Well, that's a fancy way of saying it's 2 or 3, because those are the only possibilities for z, which are between 1 and 4 exclusive. So we just add up the probability of 2 and the probability of 3, and we get 40%. Similarly, if I ask, what's the chance a randomly selected person will have at least 1 child, but fewer than 5, you'll note that that includes the events 1, 2, 3, and 4. You add them up and you find out it's 63%. Because random variables are a different approach to what we talked about before in numerical variables, everything we computed there will have an analog. Here, it may look a little different. So, for example, we make histograms of random variables. They work like ordinary histograms. The values are along the x-axis. There are 2 differences. One is you still make a bar above each value, but now that the height of that bar is proportional to the probability, not to the number of times it occurs. And this is purely a convention, whereas in statistics, numerical variables, histograms are always indicated by making the bars touch each other. To indicate you're talking about a random variable and a probability histogram, you put gaps between the bars, like in a bar chart. Let's do some examples. Here's y's distribution. The histogram has a bar for 0, 1, 2, 3, and 4. There are gaps between them, and the heights are proportional to the probability. So you can see that the height of the bar above 0 is 1/16. The height of the bar above 1 is 4/16, or 1/4, and so on. That was, I should go back and say that we used the same language to talk about the shape of histograms as we did before. It is a symmetric unimodal shape. On the other hand, z, number of children people have, is not. How would you describe that shape? It is clearly skewed right, and it appears to be bimodal. I would not call that bump at 8 a third mode, because it's very small and because it's probably an artifact of, notice, we combined everything from 8 and higher into one category because they start to get really tiny probabilities. So that bump is probably an artifact of clumping things together. But once again, 0, the bar above 0 is at height 0.27 and so forth. Finally, I left the dullest for last. When you roll a die, the probabilities are all 1/6, so your histogram has 6 bars of the same height. This is what we call a uniform distribution. Classic example of a uniform distribution from rolling a die. What is this histogram telling you? It is telling you the shape of the histogram you would expect to get if you did many trials. Each trial gets you a number, and then you made a histogram out of those numbers. If you rolled thousands of dice, you would expect your histogram to show roughly equal height bars for each of the 6 numbers. The next thing we did with numerical variables was find the mean. The mean of a random variable is the average value you would expect in the long run of many trials. That is, if you roll the die thousands of times or asked thousands of people how many children they have and then averaged all that numbers, in the long run that average should approach the mean of the random variable. How is it computed? It's computed by this slightly scary formula. Let's not get too scared and unpack it. On the left-hand side, we have mu sub x. Mu has always been our symbol for the mean. So mu sub x is the mean of the random variable x. We use the population language because one always thinks of a probability model as describing a population. Maybe that's just a convention. On the right-hand side, we have sigma, the summation notation. That's telling you to sum a bunch of things. In this case, sigma sub x is indicating you should sum one term for every value of the variable. If the random variable has values, you're going to get one term for each value. What does that term look like? The value itself, x, multiplied by the probability that the random variable will equal that value. So a shorter way to say that is you add up each value times its probability. That's actually pretty simple, despite the scariness of the formula. However, people tend to get confused about this because the formula is scary and because this looks so different but is referred to the same way as the mean we learned in earlier lectures where you just add the numbers up and divide by how many there are. So I'm going to do some examples, and I encourage you to practice this until it comes easily. It's an easy thing once you've gotten over that confusion. So here's our first example. Here's y. So its mean. We are going to add up each value times its probability. So we're going to take 0 times its probability 1/16 plus 1 times its probability 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times its probability 1/16. When we add that all up, we get 32/16 or 2. So the mean, the average number of heads that you expect when you flip 4 coins is 2. That's not very surprising, and maybe looks a little like making a big deal out of nothing. Z is a more interesting example. Z is the number of children a random person has had. So what's the average number of children an American adult has had? We take 0, the first value, times 0.27, its probability. We're converting the percentages to decimals because the percentages are just a way of writing decimals. They're a description, they're not the actual number. Plus 1 times 0.15, and so on. We add up each value times its probability, and we get 1.98. So we conclude the average adult American has had 1.98 children. I don't know if they asked only people over a certain age. Notice that is not what you'd get if you added up all the numbers from 0 to 8 and divided by how many there are. If you did that, you'd get 4. And 4 would be a silly answer for the average number of children an adult has. Whereas 1.98 seems pretty reasonable. What's going on here is that, of course, the reason 4 is a silly number, even though sometimes people have 8, is that a lot more people have 0, 1, 2, and maybe 3, and very few people have 6 and 7 and 8. So we have to weight the more frequent things more often. Multiplying the values times the probabilities does that. So the probability mean is a weighted average of the values, with the weights coming from the probabilities, and it turns out, even though it looks a little odd, to be the right thing to do. As I said, that tells you what you will expect in the long run to be the average when you do the probability model over and over again. Let me go again, do the simplest example last. X, all the probabilities are equal, so we add up each value times 1/6. Notice I can factor that 1/6 out. When I do, I get 1 plus 2 plus 3 plus 4 plus 5 plus 6, all times 1/6, or divided by 6 if you prefer. And now you notice that that's exactly our Chapter 2 version of the average. Add up all the numbers, divide by how many there are. And what we see in general is when the probabilities are all equal, so in the symmetry principle situation, this funky probability mean becomes the ordinary average that you learned in grammar school. The mean, mu sub x of a random variable, is also called the expected value of x, and is also written capital E parentheses x. This is the sort of probability theory language, which is different from the statistics language, as so often happens in this quirky field. We've already said that that quantity expected value is the average result you would expect in the long run of many tries. This is a particularly useful thing to talk about in certain random variables, namely those representing gambling and investment. Why is, say, a gambling game naturally thought of as a random variable? It's a procedure which you can repeat as often as you like. You can play as many games as you want. The outcome obviously is uncertain in a gambling game. And it's a random variable because the outcome is a number. You win a certain amount or you lose a certain amount. And if you think of losing $1 as winning -$1, then the outcome is a positive or negative number representing your winnings. So, a gambling game is a random variable. The same logic applies to investments, which work pretty much just like random variables. I mean, work pretty much just like gambling. Here's what the expected value tells you in, say, a gambling game. It tells you the average amount you'd expect to win in many plays. So you spend all night at the craps table. You'll win some, you'll lose some, but in the long run, by the end of the night, you will have won or lost an average per game that's very close to what you would calculate by calculating the expected value. That's important because, of course, the average is the total divided by how many times you played. So your net winnings is the average times how many times you played. So the really important thing in the long run is the total or average. So the expected value gives you, pretty much tells you exactly what's going to happen in the long run. So here's an example. This was taken from New Jersey's Mega Million on a day when there was a very large $12 million grand prize. And there seems to be a mistake here. This 150 shows up twice, and I'm not quite sure what it represents. But here are all the different values that you could win and the probabilities of winning them. There's a 1.3% chance of winning $2. These probabilities with the e's in them may be unfamiliar to you. This is exponential or scientific notation. It's a good way to write very small or very large numbers succinctly. What that e stands for is literally times 10 to the, meaning that this quantity represents 7.2 times 10 to the -5th. If you are not familiar with rules of exponents, there's a more concrete way to say it. E-5 tells you to move that decimal point in 7.2 over 5 places. So of course you have to fill in with 4 zeros. So 7.2 e-5 is the number 0.000072. Likewise, over at 12 million, the probability 5.7 e-9 is going to be a decimal point followed by 8 zeros followed by 5.7. Obviously, this is a more succinct way to write it. If you multiply each of those probabilities times each of those values and add the numbers up, you find that on average you win 25 cents every time you play. Of course, it costs you $1 to play. So on average, you will in net lose 75 cents each time you play. That 75 cents figure tells you absolutely nothing about what's going to happen tomorrow if you go play. You might lose $1, probably. You might win a couple of dollars, maybe. You might win 12 million, highly unlikely. But you're not going to lose 75 cents. However, if you play the Mega Million every day of your life, when you're old and gray and you look back at the times you won big numbers, the times you won little numbers, and all the times you lost, you will find that you lost, on average, 75 cents per game. That long run is the most important question for the state that's running it, or the gambling house that's running the gambling game, because they play it a lot of times. They can count on each time you play, they will win the 75 cents or whatever that you on average lose, even though that doesn't happen any particular game. Finally, we want to talk about the standard deviation of a random variable. The standard deviation, represented by sigma sub x, is given by this somewhat scary looking formula, but again, it is pretty much the standard deviation formula, but with this funky notion of averaging, right? Because we're summing over all the possible values. For each value, we take the value minus the mean and square it. So we're looking at the distance from the mean squared of each point, which is what we were looking at before. In the earlier notion of standard deviation, we average them, add them up and divide by how many there are. Here, we add each times its probability, and then we still take the square root. So it's this probabilistic version of the calculation we did before, and don't worry if it looks hard to calculate, we will never do this by hand. We will calculate the mean of simple random variables by hand, but not the standard deviation. What is important to know is what the standard deviation tells you. It tells you, again, what the standard deviation would be if you did many trials and took the standard deviation of those numbers. It gives you a long-run description of the standard deviation of the results. But what, in practice, it tells you is the variability of the random variable. So, once again, for gambling games and investments, it might be that my low-stakes poker game and my high-stakes poker game have the same average return. It may be that each time I play, I can expect to win $1 on average. But when I play the low-stakes poker game, before I get to the long run, I'm going to lose a little bit some games, win a little bit some games. I'm never going to be up and down that much. That's going to have a small standard deviation. If I play my high-stakes poker game and I'm winning or losing $100 or $200 a hand, then I will go up wildly and down wildly in my winnings before I settle down on this average of $1 per hand or whatever it is. That has a big standard deviation. When it comes to investments, if you understand standard deviation and mean, you know essentially everything that a good investment consultant will ever tell you. Why is that? Because, of course, what you want from an investment is a high expected return. In the long run, an investment with a high expected value, high expected return, will earn you more money. So in the long run, all you care about is the expected return. But in the short run, the variability really matters. So what are high standard deviation investments? They're things like junk bonds or startup companies, where you might make huge amounts of money or you might lose it all. Low standard deviation investments are blue chip investment stocks and government bonds, where you're pretty certain about the amount of money you're going to make going in. Why does it matter? Well, if you're investing for the long run, it doesn't matter very much. You just care about return. But if you're investing for the short run, if it may be you'll need to take all your money out of the stock market next year, then you could be really burned by a stock with a high standard deviation. You want, if you have a short time horizon, you want low risk. So everybody wants high return, and everybody would like low risk, but in particular, people with short time horizons really care about low risk. So, of course, because people would not invest in a high-risk investment unless it had higher return, most investments that are available to you have a trade-off, where the higher-risk investments tend to have higher average returns. So, if you are young, you have no family, and you have a reliable job, and you have good health, you're investing for the long run. You have very little chance you'll take your money out early, so you should go for high-risk, high-return investments. You should be investing in startup companies and junk bonds. Still a good idea to spread your investment around, but that's where you'll make the most money. If you are old and have a family and have poor health or a job that you could lose tomorrow, you might need to take a lot of money out of your investments right away. And in that case, you're willing to lose a little bit of return in exchange for low risk. Your investment advisor would tell that person to invest in stable stocks and government bonds and things like that. So that is most of what there is to sensible investing. Okay, here are the key points you should know from Lecture 14. You should recognize when a situation can be modeled by a random variable. It has to be a repeatable procedure with uncertain outcome, and the outcome is a number. You should be able to recognize in table form a model of a random variable, so that's a distribution, and be able to compute probabilities from it. You should also be able to check that it is a distribution, that is, probabilities are between 0 and 1, and they add up to 1. You should be able to read and interpret probability histograms. You should be able to understand the meaning of the probability mean, which is also called the expected value, and compute it in simple situations. And finally, you should be able to understand the meaning of the probability standard deviation. And that's all we need from Lecture 14.